now?
Yes.
Wonderful. Throughout my talk, I will use the so-called breaking continuous suppression paradigm as a recurring example. So I'll begin by explaining how this paradigm works. Breaking continuous suppression, or short BCFS, is a reaction time paradigm. And the idea is that it tells you how fast people can detect a certain stimulus. So you sit people down in front of a computer screen, you put their head on a chin rest, and you put a physical divider between their eyes. Then on the screen, there are two squares, and because of the physical divider, each eye can only see one of the two squares. One square will always contain what is the target stimulus, for example, a face, a spider, whatever visual target stimulus you can think of or are interested in. And the other square will contain a so-called Mondrian pattern. And as you already can see, it's very colorful. And in addition, it's constantly changing every few milliseconds. And because our brains are weird, you don't see two separate squares in your mind, you see one single square. So the target stimulus and this Mondrian pattern overlap. And then the idea that people who devised this paradigm had that you initially only see this colorful pattern because it is constantly changing and attracts a lot of initial mental resources. And only over time, this target stimulus breaks through. And then this is what you're interested in. And you can imagine that this breakthrough time is influenced by a lot of different factors. For example, the size or brightness of a stimulus, but also higher order factors such as how relevant that stimulus is for yourself or how familiar you are with it. One particularly fancy research line by Sklar and colleagues used this paradigm to claim that we can solve mathematical equations unconsciously. So what they did is they presented participants with prime, and they primed them subliminally with mathematical equations, for example, 3 + 4. Then after each equation, they used this BCFS paradigm to present participants with a number, and that number was either the solution to this mathematical equation or not the solution. For example, 7 or 8. And then what they found is that participants were faster at detecting numbers which were the solution to this mathematical equation. And from that, they concluded that participants expected seeing this solution and were therefore faster. And that they used to claim that we solve these equations unconsciously. And of course, we can do math unconsciously, sort of the dream of every math teacher, but it's also a very big theoretical claim. So people tried to replicate this finding. And there were two notable replications, one successful and one unsuccessful. And both underwent a lot of scrutiny. So eventually, somebody found a coding error in the code of the successful replication, and correcting that error led to the finding becoming non-significant. So the replication also became non-successful, and the authors decided to retract the article. Now, 2 years later, the same authors published the same paper again, based on the same data in the same journal. But now again, they said that they found a significant result in a successful replication. So then I asked myself, how is this possible? And the answer was hidden in their supplementary materials and their methods section. They changed the inclusion criteria for individual trials and participants. And while I think that's very questionable, that's not the point I'm trying to make. What I do try to show is how very small decisions you make in your data and analysis preparation process can have very large impact on your results and theoretical conclusions. Now for the next part, you will do something on yourselves. So you can take out your smartphones or your laptops. Laptops are preferable if you have them with you. And you will explore in the Shiny app I programmed together with Leonard Boltz just how big the impact of data preprocessing decisions can be. So in the Shiny app, you will analyze a BCFS dataset in which we investigated whether in-group phases are detected faster than out-group phases. On the left side, you can see that there are various input statistics you can change. You can change how data is transformed. You can change database trimming limits, for example, median, absolute deviation from the median. And you can also change minimum and maximum limits for a value to be included. On the right side, you then have different output statistics, the most important one being the results of a t-test and a corresponding Cohen's d. So what I want you to do is to go to this website. It works on the phone. I tried it at home, so I hope it works on the phone here too. and then try and find the lowest and highest p-value you can, and denote the settings you use to find that. We will take approximately 5 minutes for this, and afterwards we will see who of you is the most creative data analyst. And for the people at home, if you have a particularly small or large p-value, you can put it in the chat. And if you have any questions, oh, thank you. Now is the time to ask. But as you saw, there are many, many different ways to analyze this very basic data set. And you also saw already that they're like associated with a wide range of different results. So one question you can ask now is, do people actually use all of these different ways to analyze such a simple data set? You would surely think that researchers would sort of agree what constitutes a correct analysis, particularly for something as basic as this. Well, this is an empirical question. And I investigated that in a project with Gijs Buistra, Rob Holland, and Julia. And there we conducted a survey of there we conducted a survey of all papers which were published using this BCFS paradigm. And we coded how they pre-processed their data. So we coded roughly what type of analysis family they used. And here we were like, all variations of analysis came into one bin, all mixed models came into one bin, all t-tests came into one bin, and you can see that, of course, the t-test bin is the biggest. So across these 101 papers, people used roughly 5 different types of analysis, with most people analyzing the very skewed reaction time data with the t-test, which is assuming normality of residuals, yay. Now, because this is all very skewed, people also use transformations. So in this graph, I coded which transformation people use and which analysis people use. And here you already have 13 unique combinations of pre-processing pathway and analysis across just 101 papers. And as you saw in the app, you can also remove outliers. And for reaction time data, this is important, because you often assume that some data points are not generated by the data generating distribution, but that they reflect, for example, boredom or distraction on part of the participant. So if you code a transformation, data trimming as yes or no, and analysis coded, you already had 20 unique pathways across our 101 papers. But as you saw in the app, there are many different ways to trim data. And if you code every of these ways to trim data, you already had 46 unique pathways across just 101 papers. And of course, you can keep playing this game. There are a lot more decisions you could code. For example, if they base the analysis on the correct trials only, how they remove outliers on a participant level, or even just the exact value they use to remove outliers on a trial level. For example, 2 standard deviations from the mean or 3 standard deviations from the mean. And if you keep playing this game, I think you would arrive at roughly as many pre-processing pathways as there are papers. And that's, of course, a bit sad, because if everyone is doing something different, that means nobody really knows what they're doing or has a good argument for it. Now, sort of to check if this is reflective of other literatures too, we recently conducted a second such survey of the Simon task. And one important thing, the BCFS task was developed in 2011, so post the onset of the replication crisis. And the Simon task is pretty old, with a lot of papers being from before the year 2000. So when we did the survey of the Simon task, there was an actually even sadder picture emerging, because the BCFS people at least tell you what they're doing, even if they're all doing something different. The Simon task people just don't say what they're doing. They just report the analysis results, and then they say they did a t-test. So what we found is that not a single paper here reported doing any reaction time transformations, which is very, very unlikely. Then for outliers, 80% of papers do not report whether and if they removed any outliers. And a lot of papers reported using fixed limits. But then we looked into the fixed limits they used, and then they used odd values such as 512 or 815 milliseconds as maximum, or 240 milliseconds as minimum. And I personally can't come up with any good reason why you would a priori come up with such a weird number as a threshold. So I think there's, again, nefarious things going on. Now, BCFS and the Simon task are both relatively simple reaction time paradigms. We have like a limited number of decisions you can make. So if you look at more complicated paradigms, such as fMRI, someone did a survey and they found that there are 69,000 plausible options to pre-process fMRI data. And of course, one important thing to ask now is, are these 69,000 different options also associated with 69,000 different results? And while this has not been done for this fMRI data set with the 69,000 different options, because there would be a lot of work, you can get some evidence for that from so-called many analyst projects. In many analyst projects, the same data set is sent out to different teams of analysts, and they are asked to analyze this data set in whatever way they think is best. Here on the slide, you can see the first of these many analyst projects by Silbertson and colleagues. And they sent out a data set where participants had to investigate the research question, participants being the analyst teams, whether a skin color of soccer players is associated with how many penalties they get. And as you can imagine, those 32 different teams came up with 32 different options for what constitutes the best analysis. And these 32 different options were also associated with vastly different results. Non-significant, but they also found evidence that white players are being penalized more than colored players. And then other people found evidence that colored players are being penalized more than white players. So again, depending on how you pre-process and analyze your data, your results and theoretical conclusions might change. And now you could, of course, argue that here, these data sets or these analyst teams differ on a lot of different aspects. Here, for example, someone used a zero inflated Poisson regression, and someone else used a multi-level logistic binomial regression. So these things are very, very different. So what I was interested in is whether also alone these very small pre-processing decisions already lead to systematic differences. And to investigate that, we again took data from BCFS datasets, 10 datasets, all investigating the in-group bias in face detection. And then we pre-processed these 10 datasets in 6 different ways and analyzed it with 3 different analyses to see whether across these 10 datasets, different pre-processing decisions lead to different results. Here you can see the median F statistic by pre-processing pathway across all 10 datasets. The first orange bar corresponds to the raw data, so to data where no data transformation has been applied. The second orange bar corresponds to analysis based on log transform data, and the third orange bar corresponds to analysis based on latency normalized data. So what you can see is that removing or that transforming data leads to larger F statistics, which in turn is associated with smaller p-values. Now, the blue-orange bars here correspond to pathways where outliers then have been removed. So what you can see is that removing outliers for untransformed data increases the F statistic, and thus makes it more likely that you find a significant result. Whereas for transformed data, it decreases the F statistics. And this becomes more obvious if you look at Bayes vectors, because Bayes vectors are scaled differently than F statistics. Data transformation massively increases the vector. And removing outliers increases your Bayes vector for the untransformed data and decreases it for the transformed data. And if you have a sharp eye, you might have already seen that the y-axis on the Bayes vector graph is the log of the Bayes vector, because if you would plot the raw Bayes vector, the difference looks like this. To put it in words, the difference between the most commonly used pathway in the BCFS literature and another pathway frequently used in the Bayes literature, in the BCFS literature, is 569. So by making the very small decision to apply a transformation, you go from weak evidence at best to extremely strong evidence for your hypothesis. Likewise, if you then decide to remove outliers, which again is a valid choice, this massive Bayes vector of almost 600 gets cut down to about 80. Now, usually if you, yes?
Do you train before you transform, or it doesn't matter?
It does matter, actually. We're currently planning a research project where we're going to look at that, because in the app with which you earlier were able to play, you also have the option to change the order, and that actually, at least for this one data set, massively impacts your results. So here I first removed outliers and then transformed, because I thought it makes more sense to remove outliers based on the original scale and not based on, for example, the log transform scale. All right. So usually you don't aggregate F statistics over Bayes factors. You aggregate by means of meta-analysis and by means of standardized effect sizes. So we also conducted a robust meta-analysis with pre-processing pathway as a predictor. And we again found the same thing. Pre-processing pathway matters. So across these 10 data sets, the standardized effect size for the latency normalized data was again about 4 times as large as the standardized effect size for the raw data. So to briefly summarize what I told you so far, first, there are many different analysis options for any given data set. Second, people actually use a lot of these different analysis options. And third, these analysis options are associated with vastly different results and therefore vastly different theoretical conclusions. So now the golden question is, what should you do? How do you select the right pre-processing pathway? And for the next few minutes, I want to convince you that you should in fact not choose at all, but just assess your evidence across all possible pathways. To do that, I will quickly introduce a research project I did for my master thesis. In this research project, we decided also not to decide. It ended up running 500,000 ANOVAs instead of 7 or something. So in the project, we investigated whether face masks increase the size of the stereotype effect in emotion recognition. The stereotype effect in emotion recognition is the finding that people are faster in detecting sadness on female compared to male faces and anger on male compared to female faces. Now, there are a couple of theoretical reasons why this effect of face masks is important, related to Bayesian models of social cognition, but for time reasons, I will not go into that, and instead move on to the analysis part. Now, as we saw earlier in the survey, there are a lot of different options to analyze reaction time data. So when I was thinking about how I should analyze the data for my thesis, I didn't really know. There were just so many good options. So I decided that I wanted to try and just make a list of all options which I thought made sense. So I first thought about which decisions I need to make. And I thought that I need to transform my data or should make the decision not to transform. I should think about fixed minimum values because the human brain is fast, but not unlimitedly fast. So reaction times of say 40 milliseconds or something are likely to not reflect the process you're interested in, but more like just be the participants pressing a button to get over with it. But of course, just how fast we are is also again a matter of debate. So I decided to vary this minimum threshold from 0 to 300 milliseconds in steps of 50. Next, for reaction time data, we know that there are often outliers because participants get bored or distracted. And there are many different ways to remove outliers. And we know that one of the best ways to do so is by using the median absolute deviation from the median. Now, what I also decided to do was to vary just how many median absolute deviations from the median, because in my opinion, there's no real reason to justify why 2 would be better than 2.5 or 1.5. It's arbitrary, so we should treat it as arbitrary. So I ended up with a total of 126 combinations of pre-processing pathway and analysis, and therefore then ended up running 126 2x2x2 ANOVAs and a lot of follow-up t-tests. Now, for the pattern of results, the yellow dots here indicate pathways where my hypothesis has been confirmed, and the black dots indicate pathways where my hypothesis has not been confirmed. So you can see that for 105 of my 126 pathways, my hypothesis has been confirmed. And now the question is, what does that mean? How do you know whether there's not actually an effect present or not? And this is actually a pretty difficult question because you don't know how your p-values should be distributed if the null hypothesis